Hello, welcome back. This video is a pre-calculus 1 final review. These finals problems are taken from the handout that the Raritan Valley Math Department shared with us. These are fun, so let's get started. So question number 1 is if $3,500 is invested at a rate of 9% compounded continuously. Okay, compounded continuously. This means that I get the the PERT formula. Okay, so now I know what formula I'm using. So what is the balance at the end of 18 years? Let's tackle this first. So our principal, our P, is 3,500. Our rate, or R, is 9% or 0.09. We take 9 and divide by 100. And our T for this first part is 18 because it's 18 years. So I set up my formula that the amount equals the principal of 3,500 times e to the 0.09 times 18. And this is pretty straightforward. I put it into my calculator. I enter 3,500 times second e to the x. It depends on what your calculator does. And then times 0.09 times 18. And I get that after 18 years, my total is a very nice $17,685 and about 82 cents. 81.6. All right, so that's part A. Now let's do part B of this problem. Okay, so I need to know my principal stays the same. My rate is going to stay the same. My principal is 3,500. There we go. My rate is 0.09. My T is what I don't know. But my amount, my leftover, is triple of 3,500. And that comes out to be 10,500. So let's set up my formula. I get 3,500 times e to the 0.09 equals 1 is 10,500. Okay, so what do I do from here? The first step is I want to get e by itself. So I take and I divide this 3,500 on both sides. And luckily, I get that e to the 0.09 equals 3. Nice and easy peasy. So what do I do now? Now I use my properties of logs, and I take the natural log of both sides. Boom. And I get that, oh, T, my time was missing. There we go. Whew, that's what we're solving for. So that I get that 0.09 T equals the ln of 3. So I take and I do ln 3 on my calculator, and then I divide by 0.09, and I get that my time is 12.21 years, rounding up. So question 1 is all about this formula, P equals RT, the PERT, and that is exponential growth. Problem number 2 is deals with exponential growth as well. We're given the equation that some population, it could be bacteria, whatever, is y equals 40 e, and the rate is 2.5, or in decimal form 0.25 times t. So in part A, it asks us to find the time at the initial population. At the initial population, or the onset, our time equals 0. So we put this in, we get that y equals 40 times e to our rate of 0.025 times 0. Now, anything times 0 is 0. Anything raised to that power is 1. So e to the 0 is 1. Now 40 times 1 is 40. So we know that initially the population of whatever it is 40. Now So that's part A. Part B asks us to find the population after 50 years. And so we set up our formula as y, because that's the population, y equals 40 times e to the 0.025 times our t this time is 50. And so we put that into our calculators. We take 40 times e to the 0.025 times 50, and we get that our answer of 139.61, and that's our population, or about 140. Woohoo! So we're making pretty good progress. Question number 3 deals with that change of base. And remember, with change of base, we take anything where we had log base b of m, we pick a new base, and as long as it's the same base on the top and the bottom, the base from the original goes in the basement and the m goes up top. So for this, I'm going to choose ln as my new base. So it says evaluate log 715. Well, we can't do that with on the calculators. It won't allow us to change the base to make the base log 7, but if we do ln over ln and use the change of base property, our 7, which is the base, goes down in the basement, and our 15 goes up top. So if we take the natural log of 15, we get about 2.708, and then we take the natural log of 7, and we get about 1.946, and then we divide that out, where we take the natural log of 15, divide it by the natural log of 7, and we get an answer of 1.3916, or 2, rounding up. All right, we're making pretty good progress on this. Let's keep going. So 4 and 5 are exponential equations, and so we're going to switch, because we're going to switch gears just a little bit. But the log and exponential equations are inverses of each other. So let's start with number 4. We're told to solve 3 to the x plus 2 equals 6. Well, the first thing that we can do is we can simplify, like clean up both sides a little bit. And if we subtract 2 from each side, we get that 3 to the x equals 6 minus 2 is 4. Now what can we do with this? What if we take the natural log of both sides? Let's try that. Well, why would we do that? This allows us to bring the x that's in the exponent down in front because of the power rule with logs. So we get that x times ln of 3 equals ln 4. And we can solve for x by dividing each side by ln of 3. And if we take in our calculator ln of 4 and divide it by ln of 3, we get an answer where x equals 1.2618, or 2. And that's how we can solve for it. We use the property, we got the constants over and grouped together. And then we took the natural log of both sides because we were keeping that equation balanced, but the power rule for logs allows us to bring that exponent down in front. And from that, we were able to solve it. Now, what about 5? Let's do question 5. This one looks tricky. It says solve for ln of x minus 1 equals -1. Now we could try and use properties of logs to do ln of x over ln of 1, but that's 0. And so that doesn't work. But what we could do is we take and raise to the e both sides. We're keeping that equation balance. We're not changing, but we're using mathematical properties to help us. On the left, the e and the natural log will cancel out. We're left with x minus 1 equals e to the negative 1. If we remember, anything with a negative exponent means that it's in the basement or in the denominator. So we get x minus 1 equals 1 over e. Now we're set up. If we do x, if we add 1 to both sides, keeping that equation balanced, we get x equals 1 divided by e plus 1. That's definitely something that we can solve. So we take 1, divide it by e, and we get that that is 0.3679, rounding up, and then we add 1. So we get that our x is 1.3679. And there's our answer. So for these questions 4 and 5, we were able to use the properties of logs to be able to bring that exponent down. And with the question 5, we were able to use the power of exponential equations to break this down and solve for it. We'll have more videos coming. I hope that this makes sense and helps, and have some fun.